I want to start this deep dive with a question that, honestly, it feels really simple on the surface, but it actually kept me up last night after I was reading through these papers.
Oh, wow. Okay.
Yeah, it's about the fundamental nature of the reality we're just kind of sitting in right now. Like, what makes stuff actually stuff?
That is, I mean, that's the ultimate quadrant, isn't it? It
Yeah.
sounds like philosophy, but it's actually maybe the hardest physics problem there is.
No, really, because I'm sitting here and I'm holding this pen. It feels completely solid. I know if I drop it, it's going to hit the table with a thud.
Right.
And I know that I am me and the table is the table. We have these rigid boundaries. And I've always just assumed that those boundaries are just the rules. Like the immutable laws of physics that were written down at the Big Bang.
Right, the universe's hardware, so to speak.
Exactly. But then I read this research coming out of the Okinawa Institute of Science and Technology, OIST, and the University of Oklahoma. And it basically says, actually, those rules, they might just be a side effect of where you happen to be standing, or rather, how much space you have to stand in.
That is a really great way to frame it, because we usually think of the laws of physics as these universal constants, you know, that an electron is an electron no matter where it is.
Yeah.
But this research on what we call ennions, and specifically this new breakthrough they had in one-dimensional systems, it suggests that the fundamental nature of reality, like whether something is solid matter or just ghostly energy, is actually environmental.
Which is wild.
It is wild. It depends entirely on the dimensions you're stuck in.
And that's what we're unpacking for you today. We're looking at a really landmark set of papers published recently in Physical Review A. We're talking about this third realm of particles that completely defy the binary logic of the universe.
We are. And to really get there, I think we have to dismantle the status quo first.
Let's do it.
Because the universe we live in, the standard three-dimensional world, is incredibly strict. It's almost authoritarian in how it classifies things.
It's a binary system,
Yeah.
right? You're either on team A or team B.
Precisely. In the standard model of physics, everything in the known universe is categorized as either a fermion or a boson. There is absolutely no middle ground. It's like a light switch. It's either on or off.
So let's define these teams for everyone, because this distinction is really crucial to understanding why the new discovery is just so mind-bending. Let's start with fermions. Because these are the particles that make up me, you, the microphone we're talking into, the coffee cup.
Correct. Fermions are the matter particles, so electrons, protons, neutrons, neutrinos. Basically, if you can kick it, it's made of fermions.
Right.
And physically, they're characterized by having these half-integer spin values. But honestly, the defining feature for our daily lives is how they behave socially.
Socially.
Yeah.
I like that. They're kind of the introverts of the particle world, right? Like they have major personal space issues.
They really do. We call it the Pauli exclusion principle in physics. But yes, essentially, two fermions cannot occupy the same quantum state at the same time. They are extremely territorial. They require a completely distinct set of quantum numbers just for themselves.
I've heard this described as the actual reason we don't fall through the floor, which, you know, it sounds like hyperbole, but it's literal. Right?
It is exactly that reason. Think about it. When you stand on the floor, gravity is constantly pulling you down.
Yeah.
The only thing stopping you is that the electrons in the atoms of your shoes are pushing against the electrons in the atoms of the floor. They absolutely refuse to share the same space.
Wow.
And that physical resistance is the sensation of solidity. If fermions didn't have that strict rule, matter would just collapse in on itself entirely and you'd just phase right through the Earth.
So solidity isn't even a physical object thing. It's a rule thing. It's basically a traffic law that says do not enter.
Exactly. It's a fundamental restriction. Now, on the other side of that binary, we have the bosons. These are the force carriers. So photons, which are light particles gluons, the Higgs boson, W and Z bosons.
And they're the total opposite.
Yeah.
Absolutely no personal space issues at all. They're the life of the party.
None whatsoever. They are the ghosts of the universe. You can literally stack 1 billion photons in the exact same spot, occupying the exact same quantum state, and they won't care at all.
They prefer it even.
They do prefer it. That's exactly why lasers work. You're syncing up a massive number of photons into one coherent state.
And I guess that's why if I take two flashlight beams and shine them right through each other, they don't crash and bounce off like lightsabers. They just phase right through.
Precisely. Light passes right through light. So that is the 3D reality we're used to. You are either a rock, which is a fermion, or a ghost, which is a boson. But here is where the source material gets a bit heavy, and where I think everyone listening really needs to lean in. Because physicists started asking, why? Why are there only two options? Is that just some random decision by the universe?
It does feel kind of arbitrary, doesn't it? Like walking into an ice cream shop and they only have vanilla and chocolate. You just assume there has to be a strawberry somewhere in the back.
That is the exact question that bugged physicists for decades. And the answer actually lies in the math of what we call exchange statistics.
Okay, this is the part where I definitely had to read the notes twice last night, but I think I've got a handle on it. It's about what happens when you physically swap two identical particles, right? Like the math of the switch.
Right. So imagine I have two identical electrons. Let's just call them electron A and electron B. If I physically swap their positions, so I move A to exactly where B was, and I move B to where A was, quantum mechanics says their wave function changes.
And the wave function is just the mathematical description of their state. Okay, but if we are in 3D space, if I swap them twice, like I swap them and then I immediately swap them back, I've essentially just done a full 360 rotation. I'm right back to where I started.
And that right there is the key. In three-dimensional space, logically, the universe should look exactly the same as it did before I touched anything at all. Because in 3D, if I walk a full circle around you, I haven't changed you. I haven't tied a physical knot around you. I'm just back at the start line.
So mathematically speaking, that means the square of the exchange process has to equal 1. Like whatever mathematical change happened during that first swap, if you do it twice, it has to completely cancel out to +1.
You nailed it. So if we have a variable for this exchange phase, let's just call it x. Logically, based on the geometry of 3D space, x squared must equal 1.
And in basic high school algebra, there are only two solutions to x squared equals 1.
You tell me?
You have +1 and you have -1.
That is it. Those are literally the only two numbers that work. And that is why we have exactly two types of particles. The +1 solution gives us bosons. The -1 solution gives us fermions. The physical geometry of 3D space literally forces the math to choose one of those two discrete options.
That is just, it's disturbingly simple. The entire complexity of the universe, everything we see and touch, the fundamental difference between a laser beam and a solid brick wall, it all comes down to a basic square root problem with only two answers.
In 3D, yes. It is strictly binary because the space allows us to essentially untangle any path we take. But this is exactly where the third realm comes in. Because about 50 years ago, theorists started asking a different question. They asked, what if we weren't in 3D?
Enter Frank Wilczek.
Yes, a Nobel laureate and just a brilliant mind. He looked at the math and realized that if you artificially restrict particles to strictly two dimensions, so think of a perfectly flat sheet of paper with absolutely zero height, the rules of that swapping game change completely.
See, this is where I get tripped up. Because I would assume removing a dimension makes things simpler, not more complex. Like if I take away your ability to jump up and down, shouldn't you inherently have fewer options?
You would think so intuitively, but
Yeah.
think about the swapping action again. In 3D, if I want to swap places with you, I have options. I can go around your left side, your right side, I can jump over your head, I can dig under your feet. And if I loop around you, I can basically shrink that imaginary loop down to nothing without ever actually hitting you. The specific path doesn't really matter because I can always lift the path right over your head.
Right, because the space is wide open. I'm not trapping you in any way.
But in 2D, we are completely trapped on a flat plane. If I walk a circle around you, my path literally traces a loop on the floor that physically cannot be untied without cutting directly through you. The history of that path gets permanently locked in.
Oh, I see. It's like a dog leash wrapped around a pole. In 3D, you can just lift the leash right over the pole to untangle it. But in 2D, the leash is totally stuck. You can't lift it up because the concept of up literally doesn't exist.
That is the perfect analogy. And because that leash is permanently stuck, the mathematical system actually remembers the swap. The math no longer has to snap back to a rigid one or -1. It can actually accumulate a phase. It can be anything in between those two extremes.
Hence the name they gave them, Ennians.
Ennians. Frank Wilczek named them that because they can have literally any statistics. They can have a spin of 0.5 or 0.3 or 0.7. They are effectively part solid, part ghost.
And this is just a theory for a really long time, right?
Yeah.
But the sources we read mention a huge milestone that happened in 2020. We actually saw them.
We did. It was a massive deal in the physics community. In these highly specialized semiconductor setups, which are effectively 2D electron gases, researchers experimentally observed this exact behavior. Wilczek called it a milestone, saying we officially had a brand new third kingdom of particles.
Okay, so that sets the stage perfectly. 3D is strictly binary because the math forces it to be. 2D allows for this any behavior because of the braiding, the leash analogy.
Right.
But the new research from OIS, the University of Oklahoma, the deep dive we are doing today, it is taking this a full step further. They're going down to 1D.
The single mathematical line.
And this is where my brain started to hurt again last night.
Mm-hmm.
If 2D works, because you can braid paths around each other, how on earth can you have any ends in 1D? You can't go around anything in one dimension. It's a tightrope.
It is exactly a tightrope. Think about it. If you and I are on a tightrope and I desperately need to get past you, I can't step to the left or right. I can't jump over you. I literally have to go straight through you.
Which, for standard fermions, is totally impossible. They just bounce right off each other like billiard balls.
Correct. In a standard 1D gas of regular fermions, the particles just violently bounce back and forth. They act exactly like hard, impenetrable spheres. They never actually swap places. But the research team we're talking about, Thomas Bush, Raul Hidalgo-Socoto, and Duarte Bloom, they asked a fundamentally different question. They asked, what if the particles could interact? What if we could actually tune how much they resist passing through each other?
So they aren't even looking at the path of the braid anymore. They're looking at the actual collision itself.
Exactly. They are looking at the bare energy of the interaction. The paper actually describes a literal recipe for creating tunable anyons in a 1D space.
Tunable is really the key word there, isn't it? It sounds almost like they found a volume knob for the fabric of reality.
That is not an exaggeration at all. By carefully adjusting the external magnetic fields and the spatial confinement of this 1D trap, basically altering how tight that tightrope is, they can directly change the effective interaction between the particles.
Explain that phrase for us, effective interaction. How does changing that turn a solid fermion into a tunable enyon? I get the leash thing in 2D, but in 1D, how do you manage to be half solid?
Okay, so imagine the particles actively trying to pass through each other on that line. On one extreme end of the dial, you have infinite repulsion. They hit a solid brick wall, they violently bounce back. That is behavior absolutely identical to standard fermions. They look and act like they have that solid rule.
Got it. Hard bounce equals fermion. That's our -1 value.
On the complete opposite extreme, you turn the interaction dial all the way down to 0. They pass completely through each other like they aren't even there. That looks exactly like bosons.
Total ghost mode. That's our +1 value.
But what the researchers successfully mapped out mathematically is the vast space between those two extremes. As you slowly adjust that interaction strength, the particles do pass through each other, but they experience a phase shift, a delay, a bit of a drag. It's kind of like trying to run through water versus running through thin air.
Okay.
And the statistical description of that gas morphs incredibly smoothly from fermion-like behavior to boson-like behavior.
So in 1D, the enyon isn't about braiding spatial paths at all. It's entirely about how sticky or how ghostly the actual physical collision is.
Precisely. They rigorously showed that you can map the exchange statistics, the fundamental identity of the particle, directly onto this specific interaction strength. You can actually dial it in. You can sit there and say, I want a particle that is 30% fermion and 70% boson today.
That is just incredible to me, because in 3D, you get what you get. An electron is an electron, end of story. In 1D, you literally get to choose what the particle acts like.
Thomas Bush made a really profound point in the press release regarding this exact thing. He asked, all particles in our universe seem to strictly fit into these two rigid categories. Why are there no others?
Yeah.
And this research essentially proves that there are others, but they are completely hidden by the 3D geometry of our macroscopic world.
It's kind of like discovering that the concept of color exists in a world that only natively sees black and white. But you only get to see the color if you look at the object through a very specific, incredibly thin slit.
That's a beautiful way to put it. And the fact that it is actively tunable changes the entire game for technology. This isn't just abstract math anymore. It's a literal blueprint for engineering.
How so? Because usually when we talk about quantum stuff on this show, we inevitably end up talking about quantum computing. Is that the major play here?
It is absolutely the biggest potential application, because one of the most massive hurdles in quantum computing right now is error rates. Quantum states are incredibly fragile. If even a stray photon hits your qubit, the whole calculation just collapses. It decoheres.
The system is just way too sensitive. It needs to be kept perfectly isolated in those giant supercooled rigs.
Exactly. But any nines, especially the topological ones in 2D, and now potentially these new engineered 1D states, they are naturally robust. Remember that memory of the path in 2D we talked about?
The leash.
Yes, the leash. That topological knot makes them incredibly resistant to local errors. If you shake the sheet a little bit, the knot doesn't just magically come undone.
Right, it's locked in.
And now in 1D, this new tunability could allow us to build dedicated quantum simulators. These are specialized systems that model incredibly complex quantum behaviors that are mathematically impossible to calculate on a normal classical computer.
Because you can literally just program the fundamental laws of physics for the particles inside the simulation.
Yeah.
You can just tell them how you want them to behave today.
Yes. You aren't just writing lines of software code. You are fundamentally coding the physical behavior of the matter itself. You are engineering the statistical rules of the universe within the confines of that little 1D wire. So if you want to study high-temperature superconductivity or some strange exotic magnetic states, you can just tune your 1D onions to perfectly mimic those exact conditions.
I want to circle back to something the researcher Raul Hidalgo Socoto said in the report that really caught my eye. He mentioned that the exchange factor determines how the entire system behaves broadly. And it feels like we are really peeling back a deep layer of reality here. Because we usually look at the particle itself, the individual electron, as the fundamental building block. But this really suggests the relationship between the particles is the actual fundamental thing.
That is a remarkably deep insight. In modern condensed matter physics, an object's isolated properties are often way less important than how it continuously interacts with its neighbors. In this 1D system they modeled, the identity of the particle, whether it's acting as a solid fermion or a ghostly boson, is entirely defined by that active interaction relationship. Identity becomes completely fluid.
It's strictly situational, which is honestly a bit of a philosophical trip to think about.
It really is, and it completely validates Frank Wilczek's original excitement decades ago. When he said we have this third realm, he wasn't just casually adding a new weird particle to the zoo. He was opening a door to an entirely new way of doing physics, where physical constraints like 1D or 2D aren't viewed as limitations anymore. They are powerful tools.
Right, because I initially said 1D sounds like an absolute nightmare, a tightrope where you can't even move around someone. But you're saying that specific restriction is exactly what forces the particles to reveal these crazy hidden superpowers.
Constraint breeds creativity. Or in this highly specific case, constraint breeds exotic quantum statistics. By forcibly removing degrees of freedom, by stripping away height and width entirely, we basically force the true quantum nature of the particles up to the surface in a way that our messy 3D world just washes out.
So if we just look at the timeline here for a second, 50 years ago, this was pure, unadulterated math on a chalkboard.
Right.
Then in 2020, we finally see it physically happen in 2D space. Now today, we have a concrete recipe for 1D tunability. Where does this actually go next?
Well, the experimental race is definitely on right now. The OIST and Oklahoma team successfully provided the recipe. They drew the theoretical map. Now, the experimentalists who work with ultra-cold atoms or specialized quantum wires are going to actively try to build it in the lab.
How do you even build a 1D line, though? I mean, practically speaking, everything is 3D eventually, right? Even the thinnest physical wire still has some microscopic thickness to it.
You usually use lasers. You can carefully create an optical trap. It's basically a hollow tube made entirely of focused light that is so incredibly narrow, the atoms trapped inside it literally cannot move side to side at all. Their wave functions get completely squashed in those directions.
Wow.
So for all intents and purposes, as far as the physics is concerned, they are living in a strictly 1D universe.
And once they are securely in that laser trap, the team suggests we can just tune the magnetic interactions to see if the gas behaves exactly as the math predicted.
And if it does behave that way, we suddenly have a viable platform for simulating quantum magnetism, robust superconductivity, and maybe even entirely new phases of matter we haven't even dreamed up yet.
It's funny because we spend so much of our time and energy looking outwards at the universe. We build telescopes to look at distant galaxies and massive black holes, but it really seems like the weirdest, most alien frontiers are right here. They're just vastly smaller.
The inner space is easily just as vast and unknown as the outer space. When you really drill down and look at the fundamental rules, they're surprisingly flexible, but only if you know exactly how to manipulate the geometric stage they play on.
That actually brings me perfectly to the thought I really wanted to end on today. We spent this time talking about how 3D is strictly binary and rigid, and then how 2D and 1D are wonderfully flexible and exist on a spectrum.
Yes.
It heavily implies that what we call the fundamental laws of physics are really just local laws of dimension.
I would absolutely agree with that assessment.
So let's just get a little weird for a second before we go. If stripping away dimensions reveals these flexible enneads and this entire third realm of reality, what happens if we go the completely other way?
You mean adding dimensions?
Exactly. We live in 3D, plus time, of course. But things like string theory mathematically talk about 10 or 11 dimensions all curled up together. If shrinking down to 1D gives us tunable reality on a dial, what kind of completely impossible states of matter might exist in 4D space? Or 5D?
That right there is the stuff of actual nightmares, or I guess beautiful dreams, for theoretical physicists. In 4D space, you have even more degrees of freedom than we do. Mathematical knots literally don't exist in 4D. You can always effortlessly untie them without cutting anything because you always have that one extra spatial direction to just slip the loop through.
Oh, wow. So the braiding physics of the 2D enneads would just completely vanish again.
Exactly, you would vanish.
So it might just go right back to being a boring binary.
Or maybe entirely other, infinitely more complex structures emerge instead. Maybe there are bizarre exchange statistics up there that don't just depend on swapping particle positions, but somehow depend on the total surface area of the path swept out in that 4D space.
So maybe there's a whole fourth realm out there where particles can just casually be both solid and energy simultaneously without any artificial tuning at all. Or just something we fundamentally don't even have a language to describe yet.
Or an environment where the strict distinction between a discrete particle and the empty space around it just completely dissolves. We honestly don't know. Our primate brains are so deeply hardwired for 3D logic. We are fermions living in a strict fermion world.
Right?
We can rigorously write down the math for 4D on a chalkboard, but we can't intuitively feel it or visualize it.
It's incredibly humbling, honestly.
Yeah.
We look down at our solid hands and we confidently think this is reality. But it's really just one super specific slice of the pie.
A very, very thin slice. But I think the beauty is that, at least now, largely thanks to this brilliant theoretical work from OST and the University of Oklahoma, we actually know how to start tasting the other slices. We finally know for a fact that the binary isn't the absolute limit.
I really like that. We're not just passively observing the menu anymore, we're actually learning how to cook.
We are. And the kitchen is just starting to heat up.
Well, I think that's definitely plenty for you all to chew on today. Next time you absentmindedly tap your finger on a wooden table, just try to remember that that reassuring sensation of solidity is really just a profound lack of imagination on the part of your current dimension.
Don't tell the local carpenters that, though. They might all quit.
I definitely won't.
Yeah.
A massive thank you to the brilliant researchers at Oyas Thomas Bush and Raul Hidalgo Socoto and Duarte Bloom at the University of Oklahoma for giving us this incredible glimpse into the third realm. And a huge thanks to you for expertly walking us through the very dense math today.
It was absolutely my pleasure.
And to you listening out there, thanks as always for diving deep with us. Keep questioning the solid ground beneath your feet. You never quite know what it might turn into if you look closely enough. Catch you in the next one.